Good day. My name is Ian Oliver F. Pagne, and today I am going to present coursework 3. Let us start with objectives. The first objective is to learn and understand Hartley's law on information theory. The second one is to learn and understand Shannon's limit on information capacity. And the third objective is to be able to solve problems regarding information capacity. We will later discuss and solve a few examples regarding Shannon's limit on information capacity. First, let us define what is information theory. Information theory is concerned with the efficient use of bandwidth in electronic communications. It calculates a system's information capacity, which is dependent on bandwidth and transmission time. The number of symbols conveyed per unit time is known as information capacity, and this is commonly expressed as bitrate per second. This was made due to Hartley's law information theory. Hartley's law information theory was made by Ralph Vinton Leon Hartley in 1928. According to Hartley, information capacity is directly proportional to bandwidth and time. In this equation, we can see that information capacity is represented by I, which is in bits per second. Bandwidth is represented with letter B, which is in hertz, and transmission time is represented with small letter t, which is in seconds. So, the definition of Hartley's law information theory is that information capacity is a linear function of both bandwidth and transmission time, which means information capacity is affected by bandwidth and transmission time, in which both are directly proportional to it. Hence, if there is a change in the bandwidth and transmission time, a directly proportional change to information capacity occurs. So, here's an example. Company A is currently transmitting to Company B with a bandwidth of 5 kHz and a transmission time of 1 nanosecond. However, Company B will now require a significant increase in information capacity due to the increasing demand. Henceforth, Company A needs to increase the bandwidth and transmission time it allots for Company B to meet the demand. As you can see, Company A is currently transmitting to Company B with a specific bandwidth and a specific transmission time. Hence, it equates to a specific information capacity. But now, because Company B will now require a significant increase in information capacity, since bandwidth and transmission time is directly proportional to information capacity, Company A will then increase bandwidth and transmission time in order to increase the information capacity that B requires. Now let's move on to Shannon's limit on information capacity. This was made by Claude E. Shannon in 1948. According to Shannon's limit, I, which is information capacity, is equal to B, which is bandwidth, log 2 times 1 plus S over N, which is signal to noise ratio. To further understand Shannon's law information capacity, we will solve a few examples. The first example is this. Consider that the 0.5 MHz data stream is to be transmitted on a voice-grade telephone circuit with a bandwidth of 15 kHz. Is it possible to approach error-free transmission with a signal-to-noise ratio of 10 decibels? Answer. We first have to list down the given values, which is the maximum data rate, which is 0.5 MHz or 500 kHz, bandwidth, which is 15 kHz, and a signal-to-noise ratio of 10 decibels. As you can see, to solve for the answer, we first have to place the formula, which is I is equals to b log 2 1 plus s over n. We then plug in the values, which equates to I is equals to 15 kilohertz times log 2 1 plus 10, and then we solve for this. We arrived at an answer of 51,891.47 Hz or 51.89 kilohertz. Hence, we can conclude that it is not possible because R, which is 500 kilohertz, is greater than I, which is the information capacity. Second example, a transmission sent by company A to company B uses a bandwidth of 2 kHz and a signal-to-noise ratio of 5. What is the information capacity of the said transmission? To solve for this, again, let us first uh, keep in mind the given values, which is bandwidth, which is B is equals to 2 kHz, and signal-to-noise ratio, which is 5. To start solving, we first have to use the formula, which is I is equals to b log 2 1 plus s over n. We then plug in the values, which is 2 kilohertz for b and 5 for the s over n, which is the signal to noise ratio. Now we solve for I. After solving, we get 5,169.93 Hz or 5.17 kilohertz. Hence, we can conclude that the information capacity with the given bandwidth and signal to noise ratio is 5.17 kilohertz. Our third example is with an information capacity of 17.5 kilohertz and a signal to noise ratio of 2000, what is the bandwidth required? As you can see in this problem, bandwidth is the one required, and we have information capacity and signal to noise ratio. Hence, to solve for this, we first have to know the given. The given is information capacity and signal to noise ratio, which is 17.5 kilobits per second and 2000 for signal to noise ratio. Then, we have to use the formula according to Shannon and then input or place the values according to the uh, letter it represents. So for example, I is equals to b log 2 1 plus s over n. So we replace 17.5 kilobits per second with I. So we replace I with 17.5 kilobits per second and we replace s over n with 2000. After this one, we separate b from all the values we have in order to solve for the bandwidth. After separating b from the rest of the equation, we arrive to the equation that b is equals to 17.5 kilobits per second over log 2 times 2001. And then after solving, we get 159595.77 Hz or 1.60 kilohertz. Hence, the bandwidth is 5.17 kilohertz. The fourth example is, what is the maximum information capacity of a transmission line with a bandwidth of 3 kHz and a signal-to-noise ratio of 15 decibels? To solve for this, we first have to know what are the given. The given is bandwidth and signal-to-noise ratio. But as you can see, signal-to-noise ratio is in decibels. We have to turn this into its unitless form. Hence, we do the following. S over n is equals to 15 decibels. Then, because S over n is equals to 10 log 10 S over n, we equate it to 15 decibels. Now, we do algebra to isolate S over n from the rest of the equation. After doing this, we get S over n is equal to 10 raised to 15 over 10, which is 31.62. After getting this unitless form of signal-to-noise ratio, we can now input it in our formula, which is I is equals to B log 2 1 plus S over N. We just plug in the values, which is 3 kilohertz and 31.62, and then we arrive to the answer of 15,083.05 bits per second, or 15.08 kilobits per second. Hence, the information capacity is 15.08 kilobits per second. Now we move to the next and last question. A telecommunications company has a channel bandwidth of 5 kHz and an information capacity of 20 kbps. What is the signal-to-noise ratio in decibels? To solve for this, first we have to know the given values, which is bandwidth and information capacity. The one thing that the thing that the problem requires is the signal-to-noise ratio in decibels. Hence, we use Shannon's formula and then we plug in the given values. After this, we use algebra to isolate S over N, which is a signal-to-noise ratio. After doing this, we arrive to the equation that signal-to-noise ratio is equal to 2 raised to 20 over 5 minus 1. Hence, signal-to-noise ratio is equal to 15. However, this 15 is in unitless form, and the question is asking for the form in which it is in decibels. Hence, we plug in 15 to 10 log which over s over n, which is 10 log 15 now, and then we solve for it, which becomes 11.76 decibels. Hence, the signal to noise ratio in decibels is 11.676 decibels. Now, this is the reference that we used for this presentation. Again, my name is Ian Oliver F. Pagne, and thank you very much for listening. Have a nice day.